Alright, let's resume. First, we talked about vectors, and we talked about three important characteristics of vectors: magnitude, direction, and algebraic rules. Algebraic rules here are vector addition given by parallelogram, which is equivalent to adding up x coordinates and adding up y coordinates, and scalar multiplication. Let me just show you the second one, which is basically multiplying a real number k to both x coordinate and y coordinate. Here k is a little bit more than 0.5, so red vector became a little bit bigger than half of the original blue, and not coincidentally, x coordinate is a little bit bigger than half, y coordinate is also a little bit bigger than half. No coincidence whatsoever. Those were vector addition and scalar multiplication. Magnitude follows Pythagorean rule, the distance from the origin, as you can see here, and using using the magnitude concept, you can find out a unit vector of any vector. Any vector v is given, and let's suppose the magnitude of that vector is 17. If I divide by 17, then what is the magnitude of the new vector? 17 over 17, that's going to be 1, right? But we keep the same direction, and that kind of thing is unit direction vector, and that's how you find out unit vectors in that direction. And then we talked about the dot product. Geometrically, we can define dot product like this: v1 times v2 times cosine of theta, kind of like this when the angle theta is given. Why cosine of theta? Interesting question, but I don't want to talk about that in Calc 1 level. Let me postpone that over to Calc 3. In component form, dot products is equivalent to x1, x2 plus y1, y2. Yeah, okay. Just multiply x coordinate, multiply y coordinate, and then add them all together. That's the dot product computation. Are they equivalent? Yes, and we used the law of cosines to prove it, and that was difficult. If you don't remember the proof, that's okay, as long as you remember the dot product formula for geometry, the angle theta, and for component. Using those two, we can find out the angles. V1, V2 are given. Put those here, and then v1 dot v2 we can calculate using the algebraic expression, and then the magnitude you can use the Pythagorean formula, and you can find out cosine of theta. All you have to do at the end is to take arc cosine and you're through. That's how you can find out the angles. Now let's talk about a special case where the angle is 90 degrees, which we call orthogonal, or the angle is 0 or 180 degrees, where vectors are parallel. Orthogonal vectors, well, cosine theta is 0, so dot product has to be 0. And then parallel vectors, well, actually it's going to be a little bit more convenient to use the previous expression rather than dot product. And one vector is scalar multiplication of the other. K is positive, then the same direction, so the angle is 0. K is negative, then the opposite direction along the same line, so theta is gonna be 180 degrees. Here's a no visualization, it's a proof, algebraic proof. That too is algebraic proof. Okay. Orthogonal and parallel vectors. Okay, using that you can find x values so that the vector is orthogonal. Okay, all you have to do is put into dot product form and set it equal to 0. The angle will be then 90 degrees. How do you do that? Well, here we go. Take the dot product, multiply the x coordinate, multiply the y coordinate, add them up, and it has to be 0. From that, you can solve for x and find out what value you want. In this particular case, you only had x equal to 0. Well, is that true? Yeah, here it is. When x equals to 0, we have these two vectors. 0, 1, that's blue, and 4, 0, that's red. They're perpendicular. In this case, how about, in this case, we have to take the dot product of this one and that one, which means multiply the x coordinate together, so x times x, x squared, and multiply y coordinate, second coordinates together. Excuse me, there are too many x's, it can be confusing. The first component, we get 4x squared, and second components, we get negative 4x. Add them up, we have to get 0. This is a quadratic equation, so you can solve it. X is either 0 or 4, and that's when we're going to get orthogonal vectors. When x equals to 0, I think you're going to get a 0 vector, and 0 vector is orthogonal to everything, but a lot of people will say that's cheating, so you may have to use x equals to 4. Well, here's the visualization. When x equals to 4, yes, we have orthogonality. Parallel vectors. This vector is k times second vector, and use scalar multiplications. K times that, set each equal to 0, so 4 equals kx, x equals to k1, or maybe I'll just add one more step here. So that's k times x, and then k times 1, isn't it? So comparing the first coordinates, 4 equals to kx, here we have one equation. From the second equation, x equals to k, we have second equation. So two equations and two unknowns, you can solve it using the standard substitution method. Do it, you're going to get 4 equals to x squared, you're going to get x equals to plus or minus 2. Well, it's usually a good idea to plug everything back in and see if we have parallel vectors. And of course, you can plot them. Yeah, they are indeed parallel. X equals to 2, same direction. X equals to negative 2, opposite directions. Can you do the same thing here? Apply k, so x equals to k times this. 2x equals to k times that. You're going to get two equations. The first component, x equals to k times that. Second component is this negative 2 times k. So we get two equations here. Solving this system of equations using the standard substitution method, you're going to get k equals to 1 and x equals to negative 1. And indeed, you're going to get parallel vector like this. There are similar problems in Web of Science, so please spend some time on these kind of problems. There are some further properties of inner product or the dot product. These names are not that important yet, but if you go over to high level math, especially linear algebra 2700, these names will come back. That's why I wrote this. As for these algebraic rules, too simple. I mean standard commutativity, associativity, square is greater than 0, those kind of things. It's very simple, so at this moment they're not much of a big deal. I just wrote it for the sake of higher level course. Orthogonal complement. What is orthogonal complement? If you have a vector, all you have to do is turn it 90 degrees, positive 90 degrees, which means 90 degrees counterclockwise, because in math counterclockwise is positive direction. Then you get orthogonal complement. That's what orthogonal complement is all about. Given vector, blue vector, and then turn it positive 90 degrees, so 90 degrees counterclockwise, called orthogonal complement. The name is formidable, but all you have to do is just, well, here's a formula, x comma y become negative y comma x. With this formula you can find out orthogonal complement of anything. Is it really worthy of some example problems? I didn't even bother assigning anything. It's too simple. Not even WebAssign. Projections, on the other hand, this is not something I'd like to spend too much time on. If this university had been primarily engineering university and a lot of students are taking this course and then going over to general physics or something, then I would spend a little bit more on all this vector geometry, but not much here, so I don't really have much motivation. And this, I already talked about one question that I postponed all the way over to Calculus 3, that's cosine of theta y. Partly related to this projections actually, but as you see, I de-emphasize this topic in gray. And I have a couple of minutes left until this video recording session expires, so let me explain as quickly as possible. But if you're not following, hey, it's okay. This is not that important as far as our course is concerned. Given vector b, component of vector b in the direction of a, we can calculate like this. And then that is a size, and then if you want to get a vector pointing toward that direction, then you can use this formula to get projection. You can do the same thing for the orthogonal complement of A, so that's the component, and that's the projection, that's the vector pointing toward that direction with the size of that component. And that's about it. I'm not going to talk about this thing anymore. And that concludes the dot product business here. And if you have any further question about dot product or anything about vectors, well, probably the best way is to take Calculus 3, multivariable calculus, where we're going to do a lot of vector geometry there. Here in Calculus 1, my purpose is to cover it as briefly as possible and emphasize only the kind of topics that are directly related to Calculus 1 topic, which is basically position vector. We're going to emphasize that aspect and that aspect only in the final section of this notebook.